Hi, and welcome to this video presentation on calibrating coherent probabilistic hierarchical forecasts with conformal predictions. My name is Daan Fernandessen. I'm a second year's Master Artificial Intelligence student from the University of Amsterdam, and in this video I will show the ongoing research that I'm doing for my thesis. In this research, we aim to help decision makers make better decisions by combining the existing approaches of probabilistic forecasting, conformal predictions, as well as reconciliation. By doing this, we aim to make both valid and coherent hierarchical probabilistic forecasts, which we will explain later. The structure of this video is as follows. I will first briefly touch on the individual components, after which I will describe two frameworks and how each component fits into these frameworks. And at the end of the video, I will cover what's left to expect from this research, as it is an ongoing work. The first component is probabilistic forecasting, which provides additional information to decision makers compared to point forecasts. This additional information is needed for accurate risk assessment and is therefore essential. Probabilistic forecasts are represented as an interval of possible values with an associated probability that the actual value is contained within these intervals. These intervals are indicated by quantiles, which can be obtained in either of two ways. Either by estimating the quantiles directly, which can be done via quantile regression, or by estimating a probability function at each time step and then determining the quantiles of these probability functions. Some of the popular approaches to do this are ensembles, Bayesian neural networks, or DPR. For the intervals of the probabilistic forecasting models, it is important that they are valid, which means that the 90% interval contains the actual value for 90% of the time, and the 50% interval contains the actual value for 50% of the time. Without this validity property, decision makers are not able to trust the generated prediction intervals that are generated by probabilistic forecasting models. Here, conformal predictions can help calibrate these intervals generated by the probabilistic forecasting models in order to make them valid. There are two ways to do conformal predictions, which depend on the output of the probabilistic forecasting model. When the probabilistic forecasting model generates quantiles, the nonconformity scores of the conformal component is the distance of the observation towards the closest quantile. And when the output is a generated distribution, then the nonconformity scores are to be the probability density of the values that is estimated more likely than the current observation. A quick note though, for conformal predictions, it is required that the data is exchangeable, which is not the case for time series. However, recent work has been aiming to overcome this assumption, and therefore conformal predictions is now a viable tool in time series forecasting. Another aspect to consider is that decision makers are often interested in forecasting a hierarchy of time series. For example, in retail, decision makers are typically interested in forecasting at different granular levels, like store or country. In this setting, it is important that the forecasts align with each other in order to make coherent decisions. So a hierarchical forecast is then said to be coherent if the sum of the bottom level forecasts is equal to the total forecast. In other words, the forecast at store A plus the forecast at store B plus the forecast at store C needs to be equal to the forecast at the country level, for which the stores are in. However, often when we are forecasting each level individually, the forecasts are incoherent with each other, as we see here on the right, where the forecasts for all of the stores is not equal to the forecast at country level. When this happens, decision makers might decide to produce only 100 products based on the forecast at country level, and then there are not enough products to distribute them according to the forecasted demand of each store. This is obviously a problem, and therefore it is required for decision makers that these forecasts are coherent with each other. One way of doing this is to forecast at only one level, let's say for a store level, or at country level, and then aggregating or disaggregating the forecast to the other levels in order to create coherent hierarchical forecasts. But this approach does not use the information available at every level of the forecasts. Here, reconciliation offers an alternative where there is in the space of all possible forecasts, there exists a subspace of forecasts for which these forecasts are coherent. Then the reconciliation component of our framework transforms a set of incoherent forecasts to this subspace where the forecasts are coherent. So here y hat is a vector containing all our incoherent forecasts, and these are then transformed via an orthogonal projection onto the coherent subspace S, which creates our coherent probabilistic forecast, coherent forecasts y tilde, which in turn are also closer to our actual observations y compared to our incoherent base forecasts. In a probabilistic setting, we can obtain coherent probability distributions in a similar way by reconciling a set of samples of incoherent probabilistic forecasting distributions. And this way, by reconciling them, we get the samples which belong to a coherent probability distribution. All right, as we have now demonstrated, decision makers can benefit from both coherent and valid prediction intervals. And then a simple way to obtain both of these properties is to interleave a conformal calibration step with a reconciliation step after getting the probabilistic forecasts. We now will show you two frameworks where we show how we can combine all three of these components. In framework 1, we first perform a conformal step, and after that we perform a reconciliation step. First, we train a probabilistic forecasting model, which can be used to predict either quantiles or a distribution. Then we calibrate these predictions to obtain valid prediction intervals, and after which we can generate samples, which can be reconciled in our reconciliation step in order to get a coherent empirical distribution function, which in turn can be used again to get quantiles as a probabilistic forecasting output. Framework 2 works in a similar fashion. We first do a reconciliation step, after which we perform a conformal step, which also starts off first with training a probabilistic forecasting model, which can be used to forecast quantiles or a distribution, from which we can generate samples, which we reconcile to obtain the coherent empirical distribution function, from which we can then again obtain either quantiles or the full distribution. And then according to whichever one we choose, we can calibrate the output with a conformal prediction step. So for each of our frameworks, it is actually essential to measure a loss in both coherency as well as validity. Since both our methods are post-processing steps, the property that one method obtains might be undone by the other. And to illustrate this, we have here a base forecast generated by a probabilistic forecasting model. And here in the middle, we see the effect that a conformal calibration step has. So as you can see here, the conformal calibration step actually increases the width of the intervals, which changes the predicted distributions. And because this calibration is not equal across the different nodes in our hierarchy, the conformal calibration step might transform these forecasts away from the coherent subspace, which means then again incoherent forecasts. We can measure this incoherence as the average aggregation error of a set of samples generated from our probabilistic forecasts. And on the right, we see the effect of the reconciliation step of these probabilistic forecasts, where here it is possible that the reconciliation step shifts the mean of the distribution, making the forecast worse in order to be coherent with the other nodes. This loss in validity can then be measured as a percentage of observations contained within this prediction interval compared to the associated probability of that interval. So now that we have shown the proposed frameworks and how each of these methods can offset each other, what is left then to expect from this research? As one property might be more important than the other one for a decision maker, we plan to control the effect of the second post-processing step in each of the frameworks, which will make these frameworks more usable for the different needs of decision makers. So for our conformal step as a second post-processing step in framework 2, we can control the effect by scaling the calibration epsilon by a parameter alpha, with alpha being 0 meaning that there's no calibration happening, and alpha being 1 meaning that there's the full calibration happening. Similarly, we can control the effect of the reconciliation step in our in framework 1 as a second post-processing step by making the transformation matrix psi look more like the identity matrix. We will demonstrate the effects of both of these frameworks with different granularities of the second post-processing step in a Pareto front, which will give us an intuition of which one of these frameworks is more suitable in a general setting, as well as which one is more desirable in specific settings for decision makers. Thank you for watching. If you have any more questions about this research or would like to know how it is going, feel free to reach out on LinkedIn.